Okay, welcome to lecture 3. By now I hope the class is settling into people who are actually going to go the duration. People keep switching around, so I just want to, a lot of new people are entering, and so I just want to make sure that you know that you can access the past 2 lectures we've been given here on the calendar. Just go to go.illinois.edu/stat200. It's on our Compass site, and that's all the information that you need. Now, or else you can just look at this URL on these. I should just write it here in case you're just entering. So it's go.illinois.edu/stat200. No spaces there. So that's where you get all the information for the course, and here's the calendar for the whole semester. And that's where we post the lectures. So right now we've had what? We had some bonus work done and homework 1. Now all the answers are visible for all this, so I can't let you make up stuff if you've missed it for some reason, but don't worry. You get to drop 3 homeworks, and this stuff is just bonus. But, so starting tomorrow is homework. This is due tomorrow, and after today's lecture you'll be able to do it. So if you're just entering, please watch the first 2 lectures, and you probably want to do this review in this homework 1. So what you do is you get onto Lon Kappa, click here, and I have it open here, and this is what it's going to look like after you click on contents. You'll click on contents, and this has everything that we've done so far. So it's going to look like that for you. All right. So here's the homework assignments that homework 2 is due. If you click on it, you'll see how many. It's due Wednesday at 11:59 p.m. And here homework 1 was already due, so all the answers are available, right? So you figure, well, I don't want to do it. The answers are already available. But what I do, and this is a really nice feature of Lon Kappa, is that you can go to practice homework. Same with the bonus review exercises. The answers are already available. But if you go back to the contents and go to the practice homework and bonus review ungraded, I post what we've done so far, and it's ungraded. And I got to post homework 1. I haven't done it yet. But most of these problems are randomized. So you can do them again with different numbers. So it's great practice, and it's great practice for the exam. So if you're rusty on any of them, or you just want to make sure that you understand how to do it, you just go there, and most of them are randomized. Not the bonus review exercises that I've posted, but the homework 1 is. So you'll see new numbers, and you'll make sure that you understand how to do it. So any questions on that? All right. And please post your questions on Lon Kappa. And some of you have been sending me emails through Lon Kappa, questions, and I email you back through Lon Kappa. So check and make sure that you know how to do that. Or you could just post on the discussion board. But a problem is sometimes people give away the answers on the discussion board, either by asking a question about their specific one, and so sometimes I'll have to hide your answers, your questions and answers, if I think they're giving away the answer. Okay. Now, can everybody hear me in the back too? Can you all hear me? Okay. So today we're going to finish. Let's go to our calendar and see where we're at so far. And we start off in this class pretty fast because I want to give you a feel right away for whether this is the appropriate class for you, because it is a second semester stats class. So I just want to start in and give you a feel for what it's like, so you can just see if you have the prior knowledge to continue. So that's why we start off pretty quickly, and what we've done so far is this part, type 1 and type 2 errors in power, and we're going to finish that up today. So let's take out our notebooks, and if you haven't bought one of these notebooks here, I'll show you. Let's go to the document camera. We're going to be on page 8 here, finishing up significance tests in power, and this is what you need to buy if you haven't bought it yet. It looks like that, and it's available at IUB. All right, so let's look where we are here. And this is example 1 again. So let's read this. And so we're keeping everything the same. We're just going to increase our sample size to 400 questions. So what was this question? This was, if you recall, it was the one where I was asking my testing to see whether Talia, this little 2-year-old, is a gifted statistician or whether she's just guessing. And so the idea was we set up this null hypothesis here, and we gave her 100 questions. And from the idea is this, that you have something called a type 1 error under a null hypothesis. And then you have a competing hypothesis called the alternative. And in this case, the null is that she's just an ordinary girl, not particular, she's just guessing. She's getting, I think that she's smart in statistics and that she's getting more than 50% of these true-false questions right because she's gifted. And that's the alternative. The null is that she's just guessing. So you have these two competing hypotheses, and you set, this is an example, like as in most cases, you set particular parameters for both hypotheses. So under the alternative, I think she gets at least 60% correct. That's what I believe. And the null is that the skeptics are saying, no, she's just an ordinary girl. She can't possibly get these statistical questions correctly, and she's just guessing. So that would mean that she gets 50% correct. And of course, sometimes she gets more than that, but it's just due to the luck of the draw. So this is the probability histogram of the percent she would get correct if she was just guessing, right? Just guessing, like randomly drawing from a box that has either true or false. So each time she draws from here and gets a 1, we count it as 1 correct. And each time she draws from here and gets it wrong, we count it as 0 correct, right? And so we're just saying, okay, the probability model is 100 draws from here, and each time she's replacing the ticket because there's a 50-50 chance on each of the 100 questions. And we figure out what the standard error is under that. What you'd expect, I think most people know that you should get 50% correct. And the central limit theorem tells us that the sampling distribution of her percent, when you draw 100 times from here and add up the number of correct or take the percent of the number correct, that it follows a normal curve. And there's the square root law, that's the central limit theorem. That's probably one of the most important laws in statistics, or theorems in statistics. And the other one is the square root law, which gives us that the error scales as the square root of n here. So the bigger the sample size, the smaller the sampling error here. It depends on the standard deviation of each question, of the inside this standard deviation average is 0.5. This is a half below 0.5. This is a half above 0.5. So the typical standard deviation from the average is 0.5. Square root of 0.5 times 0.5 is 0.5. So this is just a review of what we've already gone over. So that's 0.5 over the square root of n. And then this gives you the percent as a decimal, 0.05, and we change it to a percent, and we get 5%. So now we know, okay, so that's the sampling distribution. And then what we do is under the null. And then we say, okay, we set this significance level, which is just a decision maker. Okay, if we see strong enough evidence, if she's far enough, if she gets in this area, it could be due to just the luck of the draw. But if she's far enough out here so that there's only a 5% chance that she'd do this well, or even more extreme, just by the luck of the draw, people often say that's a standard cutoff point for the null hypothesis called a p-value. You can set it anywhere you want. You set it, and you want it to be small, 5% or under, because you want to make sure that we are going to decide that she's smart when we get beyond this. And if we decide it right here, well, the probability that, oftentimes, even if she wasn't smart, just an ordinary girl, we would make a decision called a false negative or a type 1 error. a false positive, excuse me, a false alarm saying, hey, the girl's really brilliant, when really it's just due to chance variation. So we try to keep this small, right? Let's say we set it at 5%, you can set it at 1%, whatever. And then what happens is you think about well, you might think, oh, if she's on this side, if she actually scores anywhere between, 57.5 and higher, that great, we'll reject that and conclude she's a very bright girl. But the problem is that there's another type of error you can make. There's a competing hypothesis here, the alternative. So if she really does have the ability of 60%, there's also a probability distribution around that. You can think of it as her drawing randomly from a box that looks like this. And now, even when this is true, there is this error here, depending on if the curves aren't that far apart, there's an error here that would mean that we will fail to detect that she's that bright. Even though she really is, we won't pick up an effect that's really there. So there are these two types of errors, the type 1 and the type 2, and what we're trying to do is we realize everything else being equal, there's a trade-off between them. We think, oh, why don't we just make this one smaller? Make our cutoff this direction so we don't have such a big, so when she's type 2 error. So that when the alternative's really true, we'll detect it, but then you increase the probability of the type 1 error, and when she's not bright or particularly different, when she's just guessing, you're going to conclude that she's really smart. So there's two types of errors that are competing with each other. That's the idea of the type 1 and type 2 error. And then we saw, okay, so what can you do? There's different things you can do to minimize both of them. You can't just slide this back and forth, right, our cutoff. What we want to do is, what we really would like to do is place these two curves further apart, right? And one way to do that would be to say, oh, I'm going to have a different alternative hypothesis. Maybe I'll say she's can get 65% correct. Then this, or 70% correct, then this whole curve would be shifted over. But that has to correspond to reality, and I know she can't do that well. So you want the minimal difference that's important to you. And I think 60% was what I felt corresponded to reality. So I can't just change the alternative, it has to correspond to reality, even though that would make the two types of errors smaller. So let's draw in the two types of error again. We've just been calling this one the type 1 error, and the blue one we've been calling the type 2. And remember, the type 1 can only happen when the null is true, and the type 2 can only happen when the alternative is true, and this is our decision maker. So we would like to separate them, but there's another way that we can separate them, and that's by making our measurement, the evaluation, more precise. In other words, you can think of it as shrinking these curves. This is error. This is error. So making our standard error smaller, shrinking these curves. And then increasing n lowers the standard error. So we have a greater precision, greater separation of the two curves. So this is where we're at, and we're going to show you how you can calculate n to achieve whatever type 1 and type 2 errors you want, how big a sample size you need to achieve that. But first, let's just continue with this example and show you what happens, like we did the last time, we just did it in our heads. What happens when we increase this n to 100? You can see how we can make this type 2 error much smaller and increase our power of the test, which is 100%. It's the power to detect an effect that's really there. And right now, we calculated this to be 63.5. We want to increase the power. We want to decrease this. And we can do it by increasing n, because that's going to lower our sampling error, right? So the question is, let's say we change this n from 100 questions to 400. Now that's expensive. It's a lot of work. I don't even know if Talia could take it. Asking her 400 questions, that would take me a long time. So it's expensive to do this, but I want to show you, and it's it's hard, but not expensive. She's not going to charge me for it, but it would be putting her through a lot, right? To give her a little tooth, she's 3 now. It's just hard to do. Okay, but what would happen? So we went through this, and now we'll go through it. We changed this to 400. I just want you to intuitively see what would happen. You change this to 400, right? So now you have 0.5 over the square root of 400 over 20 instead of over 10. So that would change this 5% by a factor of the square root of 4 by 2, down to 2.5. So instead of having 60% be 2 standard errors away, it's going to be 50. If the standard error is 2.5, this would be 50, 52.5, 55, 57.5, and 60, so it will be 4 standard errors away. So in other words, this whole curve is shifted up. So let's do it, and you'll get a good intuitive feel for it. All right, so we are on page 8 now. So, all right, so we're going to keep everything the same. We're just going to increase to 400 questions. Okay, so that is n. This is the only thing we're doing. Will that decrease the type 2 error? Yes, it will. By what factor? Well, it's going to decrease it by what? Let's think. It will decrease by what factor? It will decrease the standard error for percent by, we'll figure it out. So the standard error for percent, remember, this is what we're going to do now. We still have, the null is this 50%. And now I want to see how far we're going to place 60% here. So our new standard error for percent is still, it's the square root of 0.5 times 0.5, the SD. We have the same true-false, which is a 50-50 chance. So that's square root of 0.25, which is 0.5. The standard typical deviation from the average is 0.5. She could get the average of a 0-1 box of 0 and 1 is a half, and she could get a half above or half below. So that's 0.5. Then divided by, this is the square root law, the square root of, instead of 100, now it's 400. So you can see we're going to be dividing by a factor of the square root of 4 by 2. So it's going to change. It's going to make our standard error smaller by 2. And now we just multiply by 100 to get, because it's a percent, not a decimal, okay? So we do that, and we get 0.5 over 20 instead of 0.5 over 10 like we had before, times 100. And that's equal to 2.5%. So that is our standard error. So to give you an intuitive feel, what that means is, here's when the null is true. The null is true. That right here, in terms of z-scores, standardized scores, that's 0 right here. But in terms of, and this is a normal curve, so here I have it divided like 1, 2, this is 1, 2, this is -1, -2. This is in terms of, this is a 2 here. This is in terms of z-scores. But in terms of actual percents on this scale, we have 50%, then we have 52.5%. You see, because it's 2.5, one standard error is 2.5%. So if I add another 2.5, that gets me 55%. And then another 2.5 is 57.5%. And here's where 60% is. It's 4 standard errors away instead of 2. And that's what our alternative hypothesis was. So now the picture looks like this. So just to remind you of what we're doing right here, we said our first step was what? We want to change, we're using this right here, this formula right here, which says what? This says this is our hypothesized value. So this is 60% minus 50%, and it's just a distance. We're trying to change this distance into z-scores, right? Into z-scores. And we can see right here, that it's intuitively, we can see that our z-scores, we'll call this ZD, This is our distance, this is our effect size in regular units, and we want to change it into z-scores. We want to match them up. And this conversion factor, the standard, is the standard error. This relates the z-score and the regular score by this standard error here. So basically we have what? So we have, this is equal to, we're going to get, this doesn't look right here. I'm sorry. It's going to look really messy. How can I change it? Okay, so I'll make this 60% minus 50%. So that's 10%. And we want to change it to a z-score. So we're just going to solve, and we know the standard error is 2.5%. These are both percents, and this is pure units. So we just want to change to this z-score. You can see it's 4, but if you didn't intuitively see that, you could just say our z-score in terms of a distance is equal to our alternative minus our null, that's like observed minus expected, over a standard error. And the standard error is a percent only because we're dealing with percents. If you had an average problem, it would be an average. If you have difference of 2%, it's going to be the difference, or the difference of 2 average is going to be. So this standard error formula changes, but it always involves dividing by the square root of n. Okay, so you can see, so here we get 60% minus 50%. That's over, these are percent, 10%, over 2.5%. And that is 4, and that's unit free. So that's our distance in z-scores. CD is equal to 4, and you can see intuitively that makes sense. All right, so now we know we have 10% in terms of our regular units, and that's 4 as a z-score. Now, when we do this, when we do our null cutoff, we're going to divide this different distance into 2 pieces, right? We're going to divide it into 2 pieces between those 2 hypotheses. And one of them, the distance of this tail will be our type 1 error, but it's also going to, like if we, like if we put it way real strong evidence, then we're going to make a big type 2 error here. So now let's just keep it at the standard. First of all, do you want to stop me and ask a question, anybody? I can't tell if you're following it. It's review for a lot of people, but I'm trying to do because we've already done this in lecture 1 and 2. But new people coming in, do you have any questions, or are you okay? Or old people? All right? It's okay? Everybody's following? All right, even if you've seen it before, it doesn't hurt to hear it again. All right, so now, now we're just going to, if we set, we're going to set, so we have n equals, that's the only thing that's different. So that changed our standard error for percent. Why don't I show you what it changed? So this is what it changed. That n changed the standard error for percent right here. Now, the z alpha is going to stay the same. So we have to find, okay, so now what we want to do is we want to set, do I have it here? I'm going to keep everything else the same. So we're still going to keep alpha equals to, maybe I should do this. We're keeping alpha equal to 0.05%, which is 5%, same as before. So z alpha is going to be the same. Do you remember how we got that? So z alpha is going to be the same. So that is the same, is still 1.65. In case you weren't here before and you want to remember how to do this, what we're doing is we're saying, okay, alpha equals 0.05 or 5% means what? Alpha equals 5% means 5% in one tail. Why one tail? Because our alternative hypothesis was that her true ability is 60% or greater or more. I don't think that she's just a very unusual girl and either gets them either, she might get her sign wrong, she knows something, she might get it 60%, but she might get it 40% or lower, that she just doesn't, she knows something, but she gets it all mixed up. That's not my hypothesis. My hypothesis is that the alternative is greater than or equal to. So that greater is 60%, at least 60% or higher. I should have put that in. I think I have it before. What I'm looking at is that it has to be greater than or equal to, okay? It's assigned. So that's 5% in the tail. So how do I get this Z alpha? My cutoff, where on here is my cutoff? If it's 5% in the tail, that means that it's 95% this way, 95% this way, and 5% that way. And just to use this table at the back of the book, which gives you the middle area, we have to draw another tail. So it's 5%. We have to divide this 95% into two parts, 90%, and we look up the Z-score for middle area equal to 90%. So if this is your first day, I'll just review that. You go back here and you look up the Z-score at the back of the table right here on page 259, and it gives you the middle area here. So 5% on one tail means 5% on the other tail, so we're looking for a middle area of 90%, so that's where I got the 1.65. I'm just rounding it. If you want to do it on the computer, like I can show you, like if you go to at home on your homework, you can do it on the computer and you can go to this p-value calculator. And you can say, okay, I want a p-value of 0.05, and I just want it in the right tail only. So compute the Z-score, and you'll get it more accurate, 1.6, and it will show you what you're doing. Okay, yes? I think you're going to have to use the table. I don't want you to, because I don't want to give an advantage to people who have certain fancy calculators, so you're just going to have to do it, just to go by the table. Oh, the table will be given on all your exams. Yeah. In fact, if you look in your notebook, you have a practice exam from last semester, and you can see what the questions look like. Yeah. What? Does the class require a calculator? Is that what you're saying? No, you can bring any calculator you want. You just can't program it or have one that connects to the internet. Okay? All right. So it's just easier if you do it this way. We're going to grade it this way. Just go by the table, okay? So now, any questions so far? All right, so let's go back to the document camera, and here we go. All right, so that gave us 1.65, between 1.65 and negative 1.65. So that's where we get this, all right? Now that we get that, let's draw it in, 1.65. So we'll draw it in here, and if we draw it in, that's between 1 and 2, right here, 1 and 2, and we'll draw it in. And this is where we've chosen, I'm just approximating it, 1.65. This is where we've chosen to draw it. So what do we have so far? Basically what we do is we have this distance, and this is our null cutoff, our decision maker, our null cutoff that you decide it's a slider. And what it does, it divides this distance between the hypothesized values for the null and the alternative into two pieces. One is Z alpha and one is Z beta. See, right up here. Okay? And Z alpha determines the type 1 error. In this case, it's 1.65 because we set this to be 5%. And now Z beta is just going to be what? 4 minus 1.65. So Z beta this distance is now 1.65 plus what is 4? It's 2.35. In other words, it's saying when this is true, this was a 0. This is negative 2.35. So this is the absolute, this is as a distance. We're just thinking of distances here. It's really going to be always opposite signs, because basically you're saying from this, you have two competing hypotheses. You're not giving this, you're trying to say, you're setting a specific alternative, and you're saying, okay, when this is true, then our null cutoff is very far away, so there's a very tiny type. We've decreased the type 2 error to just a speck here. Before, just to give you a feel for it, before we had it like this. Because we didn't have as much precision, we had more error. Our error was 5%, we didn't have as big a sample size. This distance was now only 2, 50, 55, 60. We didn't have as good a measuring device, basically. We didn't have as much precision. And now we had set the same Z alpha of 5%, but they're not spaced as far apart. They're only 2 apart. So now Z beta was very close to what the hypothesis value is. So it's huge type 2 error. This blue area is huge. So what we succeeded in doing by increasing the sample size is separating out the two curves. And so both errors are reduced. All right, so we can see that. So here we are, so that's just, okay. So then you want to find, this is our second step. This was just finding Z beta. And we find Z beta by what? Z beta is equal to ZD minus Z alpha, which is equal to 4 minus 1.65, and that's where we got the 2.35. Now, are we done? We just want to, okay, so this is the absolute value of Z beta. All right, so now, why do we care? We care because we need to get as long as we have this known sampling distribution, the whole point is to find out this area. The area, when we make a decision under uncertainty, there's two types of errors. And we just want to find out the probabilities of both types. That's all we're doing here. And so we need to, once we get this as 2.35, well, then we can figure out the area of that. We can either look it up on the table here, like we can go here and say, all right, well, now what do we want to do? So now we have a z-score of what? 2.35, or negative 2.35. If you want to look at the left-hand tail, you better say negative 2.35, and then you can compute the p-value. And there, the p-value is about 1%, or 0.9%. And there it is. It's that tiny little area there. Of course, if when you take the absolute value, you could, that's the, so we can also do this, so that's what we're trying to figure out here. If we do negative 2.3, you just have to be careful of what the picture looks like, okay? So if you go to our table, and what are we going to do? What do we want to do here? We can find, we're going to do the same exact thing. So what we're going to find beta, we want to find that little area. So we'll find beta by looking at the table. Find beta by looking at the table here. Looking at what? The middle area corresponding to a z-score. This is called the critical value, to a z-score of 2.35, right? So we just look at 2.35. We know it's going to be really little. 2.35 here, and we get about 98.12. Let's just do it in our heads and round to 98. So that means 98% is in the middle. This gives you the middle area between 2.35 and negative 2.35. So now we have between 2.35 and negative 2.35, 98%. And we just want this little area. So that's going to be 1% approximately, because that has to be 1%. So it's 100 minus, the whole thing's 100 minus 98 divided by 2. So we find, so we get 1%. That's where it is. By looking at the table. Looking at middle area on table. Any questions on that? So now let's just write this all down nicely now. So that means that this is 1% here. This is called beta. This is called alpha. So alpha is equal to 5%, and beta is equal to 1%. Look at this. This is really good. Both types of errors. This is the type 1 error, and this is the type 2 error. Both types are small. I mean, this one kept the same, but this one got really reduced by increasing the sample size. So what's the power of the test? The power of the test is the power to detect a difference that's really there. So this is 1%, and so the power is everything to this side. It's 100% minus beta, which is equal to what? 100% minus 1%. So we have 99% power. All this, that's a hugely powered test. Very high power to detect an effect that's really there. So if I gave Talia 400 questions, I'd have an enormous amount of power to detect. I'd have a very much better measuring instrument. More questions, less variability. So I could detect a smaller, that difference with greater probability if it was really there. So that's the idea. All right, so this is very intuitive here, and so now let's move on. And we don't have, let's see, any questions so far? All right, so now this is like the homework you've already done, but let's just make sure you understand it. And this is like homework 1, number 2. And let's just look at this example. This is an example which involves averages instead of percents, so the standard deviation has to be given to you. The standard deviation of the population has to be given. You can't calculate it from the model like you can with any kind of percentages, right? All right. So let's look at this. So it's easier, actually. You don't have to calculate any standard error except SD over root m. So a large class, this is page 9, at a large Midwestern university claims that the average student only needs to spend 6 hours on their weekly homework assignments. And they claim that the standard deviation of this population is 4 hours. You believe the true class average is much higher. The people, your friends, are spending a lot more time on homework. So you think the standard deviation is about the same, let's say, but you think they're spending at least 8 hours, that the curve is shifted over. So to test their claim, you plan to randomly sample 25 students from the class of 2,000 students and ask them how many hours they spend on their homework per week. So that's the idea, a very simple standard problem. Okay, so the null hypothesis, is the professor's claim, is that the average in the population, so this in the whole population, so we use Greek letters for that, is 6 hours, with a standard deviation in the population, we'll call it sigma for the population, Greek letter is 4 hours. And the alternative is that the class population average that you're claiming in the whole population is at least 8 hours, so it's directional again, with a standard deviation of the same standard deviation. So now, if you want to understand, like all statistical tests are based on probability models. So I just want you to get, because you're going to have to when things get more complicated, I mean, these are simple models, you're going to have to like figure out what to do, whether it's appropriate to do a test or not. You have to figure out, like, translate the random aspect of whatever situation you're in into some kind of probability model, especially if you want to simulate stuff. You have to figure out what's varying, what's going on. That's what statistics is all about, is measuring variability. So this is just getting you used to that in a very simple way. All right, so formulate the null hypothesis in terms of these simple probability models. So the null is what? That pretend that all 2,000, I'm just saying there's a random draws from a large box is a very typical thing to do, this box model. It's a common term, and it just means it's this simple probability model that involves writing numbers on tickets and a procedure for randomly drawing them and computing some statistic. So what we're going to say is we're going to model this as if, what? There's 2,000 students in here, 2,000 tickets in the box. On each is written a number indicating the number of hours per week each student studies. So 2,000 tickets on each is written number of hours that the student typically spends per week. Okay, so on their homework. So the null hypothesis is, the professor claims, that the average inside this box is 6 hours, mu is equal to 6 hours, with a standard deviation, sigma, known standard deviation of 4 hours. So that's your null. And then what are we doing? The null hypothesis is that we are going to be randomly drawing from here how many times? How many tickets from here? We're going to sample how many? Draw, where is it? Where did it say? I can't even, oh, right here. Randomly draw, n, that's what your n is, always, your sample size. This number doesn't enter in at all to the calculations. So randomly draw, n equals 25 tickets, and this time, I mean, if you're going to be really careful about this stuff, you should specify whether it's with or without replacement. And because that will change it slightly. If you're doing it without replacement, it reduces the standard error a little. We're not going to worry about that calculation, but later on you might. So it's without replacement because we don't want to sample the same person twice. Okay, it's just being careful about this. All right, which is different than the Talia problem, where each time she reached into that box represented a question where the odds in the null was a 50-50 chance. It didn't change. Here we're only sampling 25 out of the 2,000 tickets, so it's not going to change much. But if we took out every ticket, there'd be no standard deviation. We'd always get the same thing. So, and we took the average of the tickets, there'd be no sampling error, right? If we took out 2,000 tickets. So it reduces it a tiny bit because 25 is small compared to 2,000. All right, so we've got that. And now let's do the alternative. Now I kept it really simple. The alternative is almost the same thing. Here's the alternative. And we still have, the alternative is that we think that there's still 2,000 tickets. On each is written a number. We're still going to randomly, this is for both of them, we're still going to randomly draw 25 tickets without replacement, but we think students are spending a lot more time, that it's not 6 hours, that the average of those 2,000 students, mu, is actually equal to at least what? 8 hours. And that's a big difference. And we think we can pick it up with a sample of 25. All right? We hope. And we said this is the same. So that's the idea. All right? So you're going to draw two different sampling distributions of the average of 25 draws from here and 25 draws from here and see what they look like and see what the type 1 and 2 errors are going to be. So under the null hypothesis, this one, you'd expect the sample average, this is called x bar, I'm trying to get used to this notation here, x, the Roman letter, bar for average, equal to what? Well, common sense, the expected value, if the population is 6 hours, population average is 6 hours, wouldn't you expect your sample average to be 6? What else would you expect? Right? Okay. Average mean is the same thing. You can say population mean, population average, same difference. Okay, so this is 6 hours. And under here, the alternative, you'd expect it to be 8 hours for the same reasoning. Your sample average when you draw 25 tickets out of here. Now the typical variation, the sampling error, think of standard error as sampling error of the average. Every time you take an average, you're not going to get exactly 8 hours from here, even if it was true, and exactly 6. It's going to vary. And that variation is given by how much variation is inside the box. The bigger the standard deviation. If there was no standard deviation, that would mean every single student gave the same answer of 8 hours. And you'd have no sampling error, because every ticket in here would have 8 hours. So of course, the bigger the standard deviation inside the box, that's what this is, the bigger your error, right? And then the bigger your sample size, the smaller the error. Because when you take a lot of tickets from here, you're going to get more accuracy the bigger your sample size. You all know that, more precision, right? If you just sample one person, it could vary all over the place. It would vary by that much, give or take that. But each, if you take a whole bunch of people, each time more people and average them together, you get more precision. You more precisely estimate. You have less error. Okay, so that by that formula. So this is super easy. The standard error of the average, which is the first thing we should do, is just going to be 4 hours over the square root of what? 25. And so that is 0.8. So now, look what we have. Basically, we have everything we can answer. We have everything here. We can right away solve for z beta, right? But I want to show you the intuition first. But we can right away solve for z beta because look what we have. We can just fill it in here. We have 8 minus 6. That's 2, right? And then if you fill in the z alpha, we'll have to figure that out, right? But we can. I think it's going to still be 1.65, isn't it? We're keeping it at 5%, so it will still be this. Plus, then we'll have the absolute value of z beta. Just remember to keep it positive, and then you don't have to worry about this, just z beta. And then times 0.8, you can solve for z beta. All right, but let's go through it and draw the picture, just so you get a good feel for what's going on. All right, so the center, and you have to understand the logic behind it and where this curve's coming from and everything. I mean, these are all the important ideas in stats, and that's why I'm starting off with this problem to review them all. Okay, so the central limit theorem tells us that the sampling distribution of the average will follow the normal curve as long as n is large enough, even if this is completely not normal. And clearly it can't be normal because look, it's not going to be symmetrical because if you go 2 standard deviations above, you get 6 plus 8 is 14. But if you go 2 standard deviations below, you say 6 minus 8 is -2, and nobody studies -2 hours. So it's a skewed distribution. You know it's not quite normal. So, but let's just to say that it's assume the class distribution of study hours isn't too far from normal, isn't insanely skewed, so that the central limit theorem will kick in after 25 draws. So it'll draw the sampling, so we're going to assume that. And if we wanted to be really careful, we could simulate this. We could make up a distribution of typical scores, see how far it is from average and so forth. But right now, we're just going to try to get the basics down. So you draw the sampling distribution of the average under both conditions, and we'll label the null cutoff. Significance level, we're keeping it at this right here, what we've been saying. And then draw the sampling distribution the other way. All right, so what we have here is what? So we know that when the null is true, it's 6. And we know in terms of a z-score, it's 0, right? And now we know that we've got this 0.8. So we can say, okay, 6.8 corresponds to 1 standard error. and then you add another 0.8, and you'll get 7.6 corresponds to 2. Then we'll add another, and we get up to 8.4 corresponds to 3. So we can see that right here is where 8 is, where our it's going to be 2.5 apart. But if you didn't draw it out, you could figure that's probably the easiest way to do it. So let's just translate. First, what we want to do is we're going to get this ZD here. So we'll say, okay, ZD is equal to what? It's going to be equal to this distance, 2, divided by 2 hours divided by 0.8 hours. These are hours, and then we get these pure units, which is 2 divided by 0.8 is 2.5. And that agrees to with what we just drew here. So let's just draw, okay? And now we're going to draw right at 8 here. We're going to draw another curve. Okay, so let's make another curve that's the same shape, centered right here at 8, just so you can get a feel for this. All right, so now we have this distance here between 8, we know right here, between 8 and 6, this distance of 2, in terms of a, like this is where your hypothesized value of the null is. And here's your, see it's dead center, hypothesized value of your alternative. And we said that this distance right here, this distance is ZD equal to 2.5. All right, and now we're just going to cut it into 2 pieces with our null cutoff. And again, we're going to do the 1.65. You could choose anything, but you can see that if you do this at the 1.65, so we'll do that, and this is going to be our null cutoff right here. We'll just estimate it at 1.65. So that's our null cutoff, and you can see that what? That from here to here is Z alpha, that's 1.65, and from here to here is Z beta. So what must that be? 1.65, that's Z alpha, plus Z beta, these are absolute values, plus what? Equals 2.5, right? So Z beta has to be 2.5 minus 1.65, right? 0.85. Those are absolute values. So our next step is to find Z beta, and Z beta is equal to 2.5 minus 1.65. That's what we just said. And now our last step is to find beta. So what's beta going to be? Do you know what we're going to do to find beta? You're just going to look on this curve, and you're going to say what? You're going to have to look at that, look up this, Z equals 0.85. Let's do it. 0.85, and we get about 60. Let's just round it, because we're going to do this in our head. On your homework, you have to do it more accurate. 60 in the middle, so that will be 20 on each tail. And make sure it looks about right. So to find Z beta, what do we have to do? We have to look up 0. Just did it. We got, whoa, I drew it badly. I didn't make that look like 60%, did I? If I drew it here, actually I'm not that far off. It's very deceptive because it's so high in the middle. If I drew it here, it would be about 60% in the middle. 60% in the middle. This is between 0.85 and negative 0.85. And so we have 20% and 20%. So what do we have here? let's just make sure we've got this correct. How do you know how to draw these things? This right here is when the null is true. So just look at this, right? This is your 5%. Okay? And that's alpha. We set that. Alpha equals 5%. Now we're on this curve, when this is true. So trace this curve. When the alternative is true and they're really spending 8 hours, if we decide for the alternative only when it's on this side, even when the alternative is true and they really are spending 8 hours, look at all the time that our test is not going to pick it up. So I'd be worried, look at all this time that our test, even if we were right, what percent of the time will we be wrong? And that's called beta. It's not that bad, but it's 20%. And the power of the test then is equal to what? 80%, which is about what granting agencies want, at least 80%. They usually say, we'll look at that in a minute. All right, so I think we finished this problem. Now, let's see. This is calculating beta for a two-tailed alternative hypothesis. Can we skip this for next? Let's just, since your homework isn't doing this yet, I want to show you how to do it if there's a two-tailed alternative. But I think what we should do, because we only have like 20 minutes left, let's go, we'll get to this. But let's first, I want to make sure you have enough to do your homework. So let's turn to page 11. Okay. And then we'll go back to that. So now, how many people do you need to sample to test the effect size? All right, so now this is the much more usual direction that you're going into. Let's read this together. In the previous examples, you were given the sample size n and asked to calculate the size beta, the type 2 error. But in planning a study, you'll need to calculate how big a sample you'll need to detect the effect you're looking for at set levels of alpha and set levels of beta. Now, this is one of the single most important things you can do if you're a consultant, is get this right, figure out how big a sample size. So most granting agencies request that you plan your studies with alpha equal to less than or equal to 5% and beta less than or equal to 20%, which means a power at least of 80%. In other words, you need to find the smallest sample size that will detect an effect at least as large as the one you specify in your alternative, given the type 1 and type 2 error limits conventionally set. Because they won't fund you if you have an underpowered study. If it's underpowered, they're not going to say, why should we give you this money? You don't have the power to detect the effect if it's there. And then if it's really overpowered, they're saying, wait a minute, we don't need that much power. That's a lot of money. Like if it's 99% power, they usually don't want. Well, it depends on what you're doing. Okay? So how should you choose your alternative? First of all, the specified alternative. These are in all these cases, all these power calculations where we really have to calculate things, have a whole range of alternatives. And we have to specify the smallest one that matters to us, as opposed to the diagnostic tests where there's just one alternative, right? You have the disease or you don't. Or a fire, the fire is there or it's not. Okay. How should you choose your alternative? As we discussed earlier, that depends on what difference you care about. What's the minimum difference that's important to you or whoever wants you to do this study? So in example 2 on the previous page, how big a sample would we need if we wanted to get 90% power? Let's say we wanted higher power. And we're wondering, how big a sample do we need? We saw with 25, we only got 80% power. So we want to plan it better. Maybe we want 90%. So what would we do? Everything's the same. Now, what changes? Well, the idea is that if you specify the power, then you can figure out Z beta, Z alpha, you still have all this. Look, you still have the same thing, 8 minus 6, right? Now, before we had to figure out z beta because we knew this standard error. Now we don't know this standard error. What we're going to have to do, but we do know both of these. Like with 5%, we already know that z alpha is 1.65. Now we can get this beta. Let me show you z beta. You can get it from the power is 90%. Just think, if power is 90%, just draw a picture, right? Power is 90%. That means from here on in is 90%, and you want this error of 10% here, right? Right? So so beta is 10%. Now what's the z beta? This is kind of hard. It's a bad way to draw it. I'll do 90% this direction because it goes all the way to the tail. Now if I'm going to be finding a middle area here, it's not going to be, the z beta is not going to correspond to 90%. What is it going to correspond to? I have to put a 10% on that side. So I have to divide this 90% into two parts. That means 80% in the middle. So now I want to see what z-score corresponds to 80% in the middle. Does this make sense? So I'm going to go look for that, right? Because it's 90% all the way to the end. Just to use this table, which is a convenient way to think of it anyway. All right, so now I want 80% in the middle. So I'm looking for a middle area of 80%. And let's just round it here. Just go to the closest line on the table. So we can just do this in our heads. And that's 1.3. Okay? It's going to be somewhere between 1.25 and 1.3, closer to, but let's just round to 2 instead of looking at, okay, so 1.3. Is that okay with everybody? So that, if you look at it, it's between, it really is over here, negative 1.3 and 1.3. So let's just remember that we just want the absolute value. We want a distance. So that's going to be 1.3. So that's what this is, 1.3. That goes right in there. So now we have that. And now, standard error. Well, the standard error of the average is SD over root n. SD is still 4 hours. And now we have the square root of n. And all we're going to do is solve for n. Does everybody see? We're using that same formula, which says your hypothesized, your effect size you want to detect. This is a distance of 2. This distance of 2. Now you're trying to match it up with this distance in standard units of 2.95. Okay? And you're just figuring out how, you just say, how small should my standard error be? I want to reduce my sampling. I want to get my standard error just right by adjusting my sample size. I can't adjust the standard deviation of the population. This is my only adjustable parameter, so I am going to adjust that to make it all matched up. So then we can just do this and solve for n. So what can we say? The square root of n is going to be equal to, we'll add those together. What's that? 2.95 times 4 divided by 2, right? So that's 2.95 times 2, which is 5.9. So then we square both sides. Okay, and I don't know why I put parentheses around there. Okay, and when I did that, I got 34.81. That makes sense. 6 squared is 36. All right, and you want to round up, because these are people, so round up to the nearest integer, unless told otherwise. That's what people do. So even if it was 34.1, you'd round to, generally speaking, to 35. Unless, in the directions in the homework, I might have to tell you to round, just round to the nearest whole number, not round up. All right, so now I wanted you to repeat this with the two-sided. So do we have time to do the two-sided? Or we could go it on into, yeah, we have time to do the two-sided now because we have like, so let's go back and I'll tell you the difference between, any questions on this? This is really easy. Just to give you a feel for what you're doing, if you went to the page 13 with the summary, to calculate, up until this point, we calculated the type 2, we calculated beta, the probability of the error, for a given n, right, in a set alpha. Now, and so we know what we did was we know this. Here we knew this, the standard error, because we knew n. We knew this, and we were trying to figure out z beta. And from that we got beta. Now, this is much more common. You're going to calculate n for set z alpha and z beta. So these are going to be set by your power, by the whatever power specified. This is going to be set. And now you just have to substitute the correct standard error formula, like whether it's for an average, whether it's for a percent. And the last thing we're going to do is look at the difference between two. Like if you're comparing two samples to each other, the standard error of the difference of averages or difference of percents. And we'll do that. The homework on that isn't due till Monday, so we'll save that. That's this problem. We'll save that for, we won't do this page today. We'll do that later, but let's do this. So what happens when, this is very easy. So here we are back on page 10. So now you have these, often people like two-tailed hypotheses. So we're on page 10 now. So when we set alpha equal to 5%, we set the probability of rejecting the null at 5%. For a two-tailed test, that means 5% is now distributed between two tails, 2.5% in each tail instead of one, which would mean 95% would be in the middle, which would correspond to whatever z-score, like about 2, instead of 1.65. Let's work through this, and I'll show you what I mean before we start doing this. Okay. So let's just, here, in Stat 100, I think we skipped this. So a lot of you have had this, but people in Stat 100 haven't, maybe. So I just want to lay this out. So you want to, let's say, finding the z-score, z alpha, the critical value of z is what they call it, at alpha equal 5%, let's say, at alpha equals 0.05. And you can change that for both, let's say, for the one-tail test. You already know that one. It's just super easy. We've been doing it. It just means 5% in this tail. That's all it means. And so we had it looking like this, right? And then that means we have to draw another 5% here. And then 90% is in the middle, and then we look up the z-score, and that's where we get this. Okay, now what happens for the two-tail test, which is super common? They like to do lots of people like to do two-tail tests. Okay, so for the two-tail test, which would mean what? We'd perform a two-tail test if we thought the true class average was far away from what the professor claimed, but we weren't sure in which direction. So it would either be, our hypothesis would either be it's greater than 8 hours, or greater than or equal to 8 hours, or less than or equal to 4 hours. That doesn't really make sense here, but we'll do the calculation anyways. I mean, it makes sense, like in our example, what we're doing right now with you guys, the experiment. I don't know if the online or the in-person is overall better. I don't know. I think they're probably the same. I don't know. I really don't. But that's a two-tail test because I have no hypothesis about which direction overall is better for everyone. I suspect it doesn't make any difference, but I'll do a two-tail test for sure. You see? So there's lots of cases where you do the two-tail test. So then what does it look like? Well, then, instead of having 5% in the tail, because you know it's going in this direction, you have enough information to say that, you don't know which direction it's going in. You're just testing whether it's different, whether the two things are, whether they're different. And so then you have a two-tailed test, and that 5% is distributed between two tails. So it's like either out here or here, and this is 2.5%. And we're actually, we don't know which direction. We're in a situation where we don't know as much. So we need stronger evidence to reject the null. We have to go further out. And then there's 95% in the middle, and z is equal to, we look at 95% in the middle. And so we'd go here, and it's going to be between 1.95 and 2. And some of you probably know it's very close to 1.96. But when people are estimating things, they always say 2 sigma. So for now, we're just going to, you won't be marked wrong, and certainly sometimes I'll tell you whether it will be 1.96 or 2. Okay, for now, let's just, to do things in our head, let's just say it's 2. So that's between z is 2 and z is equal to -2. All right, so now we can just do the same example again with the two-tailed test. And you'll see that you're going to need stronger evidence to reject the null, which will make your other type 2 error bigger. Okay, so now, which corresponds to, approximately 2, 1.96. Instead of 1.65 as above. Once the alpha is set, z beta is always one-sided, because whichever side you calculate it on, whichever way it lands, like your type 2 error is always one-sided. It's always going to be the overlap, and the overlap only happens in one direction. Okay, so now we'll set this up. So calculate the probability when it's two-sided. So everything's the same. Everything's the same. So this is the first example we did with the 6 hours. That's 0 here. And then we had 6.8. Remember, it was 7.6 all the way. 8 is up here. Excuse me, 8's not there. That's 8.4. And 8 is right here. Oh, wait a minute. Okay, so 8 is right there. So if we're doing 6, 2.5, right? So we have this one, and we have, so this is all the same. That's 8. That's supposed to be right here in the middle. I'm rushing, and I'm a bad artist when I'm rushing. I'm not a good artist at any point. I just want it to look exactly like before, right? But now, and so this is 0, this is 1, this is 2, and this is 2.5, which is our ZD. So from here to here is ZD equal to 2.5. Right here. You know, this is hard to see. I'm going to put it up here. So we have this and 8. Here, I'm just going to put it up here. It'll be much easier to see. Okay, so here we still have what? We have from here, ZD is equal to 2.5. That hasn't changed. All right, but now Z alpha is going to be 2. So now we're going to have our null cutoff be at 2. So that's right here. So this is where our null cutoff is. So now you have Z alpha equals 2, which means Z beta is equal to what? 2 plus what equals 2.5? 0.5. So Z beta is equal to, all right, so it's the same thing here. So why don't we just put it down here? Our first step is still that we got the same distance. We have 2. 8 minus 6 divided by 0.8, we have 2.5 as our distance as before. And our second step is what? Z beta. Z beta is going to be equal to what? ZD minus Z alpha. ZD, excuse me, which is 2.5, the same as before. But now what goes in here? 2. So it's 0.5. So that's what's different. Now, this is the only difference. The alpha is equal to 2, not 1.65. So that makes the beta smaller. So we have this. So we have this right here. Can I show it to you? Let's see. Our cutoff is right here. So this is 2.5. Just so you can get this is 2.5% because it's two-sided. And now look what happens to this. What is beta? How are we going to figure that out? Well, it's going to be much bigger. It's all this. So let's figure it out. And so how can we figure it out? We can say between negative, sorry, thank you very much, negative 0.5 and 0.5, this is Z beta, we want to figure out this area here. So we look up 0.5, and I looked it up, and it's 38%. It's much smaller. That means 62% between the two tails. So this is 31%. It's still less than 50%, but it's gone up to 31%. Does everybody see that? 31%. So this is equal to 31%. So our power to detect that difference is lower. That's 69%. So to achieve the same power that you have with the one-tail test, you'd have to increase n. Okay? It's just a higher standard, which is why so you'd need a bigger n. It's a higher standard, which is basically why everybody does the two-tail test. They just want more stringent requirements. There's too many ways that people can cheat with the one-tail test. They pretend, so they usually just, no matter what the situation, they usually want you to do a two-tail test, even if it doesn't make sense. They just basically want more stringent requirements. Yes?
Why did you choose H8 to be 4 hours instead of 8 hours?
Why did I choose what?
Why did you choose H8 to be 8 hours?
8 hours. I'm keeping the same exact problem we just did. I'm doing the same exact. I'm doing this.
Why is greater than 8?
Oh, I see. Greater this. I'm showing you either. If you're doing a two-tailed test, it would be the same on either side. So you could be either greater than 8 or less than 4. It's the same idea. Excellent question. Yes, it would be the same calculation. I just drew one picture. Thank you. Excellent. It could be on the other side. Thank you.